Hey there guys, this is MathCamp321 presenting a video on solving rational equations. In this video I'm going to give you 6 examples of how to solve rational equations, and the key concept to keep in mind here is to find the LCD of your denominators and then rewrite each fraction with that LCD. So let's look at example 1. In example 1, as I scan through the 3 denominators, I see a 28, a z plus 2, and a 4. So my LCD is going to be 28 times z plus 2. So what I'm going to do now that I've established the LCD is I'm going to rewrite each of the 3 fractions with that LCD. Okay, now that I've set up my 3 fractions, I've got to ask myself a question. And that question is, how do I get the old denominator of each fraction to look like the new LCD? So as I look to the fraction all the way to the left, I have a 28. But I need to introduce to that 28 a z plus 2, which will give me the LCD. So I'm going to introduce a z plus 2, and I'm going to write that on the top in parentheses. Now I'm going to distribute the 9 through the z plus 2, leaving me with 9z plus 18. Let's move to the middle fraction. The denominator of the middle fraction currently says z plus 2, so it's missing the 28. So I'm going to multiply the 3 on the top by a 28 to introduce a 28. Now 3 times 28 is 84. Now let's move to our rightmost fraction. The rightmost fraction currently has a denominator of 4. It's missing a 7 and a z plus 2, so that's what I'll need to introduce in the numerator. A 7 and a z plus 2. Now, 3 times 7 is 21. 21 multiplied into a binomial means I'm going to distribute, and I'm going to get 21z plus 42. It's worth noting that when you're working with a problem that has both z's and 2's in it, that you really make them distinguishable so you're not confused. So what we've done effectively is we've rewritten each fraction so that it has this common denominator. Now the next step is pretty fun. I'm actually just going to cross out all 3 denominators. And what I'm going to do is solve the resulting problem that exists in the numerator. So what we have is 9z plus 18 plus 84 equals 21z plus 42. This will be 9z plus 102 equals 21z plus 42. Subtracting 9z from both sides, we end up getting 12z. And subtracting 42 from both sides, we end up getting 60. And if we divide both sides by 12, we end up getting that z is equal to 5. Okay, now it's really important in problems like this that you check. And what you're looking for mainly is that when you plug back into the original problem, you do not end up with 0 in the denominator. And the only potential for that to happen would be in the middle. If we look at the middle fraction, if z were negative 2, you'd end up getting an undefined situation. But luckily for us, z is not negative 2, it's 5. So we should be fine. So the answer to number 1 is z equals 5. Let's take a look at example 2. As I scan through my denominators in example 2, I've got a 24, a 3 minus x, and a 4. So the LCD is going to be 24 times 3 minus x. So what I'm going to do now is set up 3 fractions, each with that LCD. Now I'm going to ask myself, what will I need to introduce to each fraction to make the old denominator look like the new one? If we look to the fraction all the way to the left, the denominator is currently 24. So I'm going to need to introduce a 3 minus x. And then I'm going to distribute that 5 through, getting me 15 minus 5x. In the middle, we have currently a 3 minus x in the denominator, so I'm going to need to introduce a 24. 2 times 24 is 48. Now when we move to the last fraction, our denominator is 4, so I'm going to have to introduce a couple of things, a 6 and a 3 minus x. Now 1 times 6 is 6, so it's like a 6 on the outside of the binomial 3 minus x. When I distribute, I end up getting 18 minus 6x. Now for the fun part. Now that I've rewritten each fraction with that LCD, I can merely cross the denominators out. This leaves us with 63 minus 5x is equal to 18 minus 6x. Adding 6x to both sides, I'm left with just x on the left. And subtracting 63 from both sides, I'm left with negative 45. Now we need to take our answer and at least for a moment consider whether this is going to produce a situation that is undefined. So again, I'm looking at the denominator in the middle, whose denominator is 3 minus x. Now the only problematic x would be if x were 3, because then you'd have 3 minus 3 or 0 in the denominator. But that's not the case here. We have negative 45, so we should be good. Let's move to example 3. Now there's a couple things I need to do before I start example 3. The first of which is I'm going to take that first term r and I'm going to put it over 1. And the second thing I'm going to do for the second fraction is factor that denominator into r plus 1, r minus 1. And now I'm going to establish the LCD. And the LCD is going to be r plus 1, r minus 1. Or, if you kept it FOILed, it would be r squared minus 1. Okay, now I'm going to rewrite each of these fractions with that common denominator. Okay, now we've rewritten each fraction with the same denominator. Let's figure out what the numerators are going to be. If we look at the fraction all the way to the left, all we have is a 1, so we have to introduce everything. And the easiest way to think of everything is r squared minus 1, because I have to introduce an r plus 1 and an r minus 1, and that's really just r squared minus 1. So if I have to distribute this r into the r squared minus 1, I end up getting r cubed minus r. Now if I look to the middle fraction, the denominator is exactly the LCD, so I don't have to introduce anything. So I'm just going to rewrite the numerator, r squared minus 5. Now as I look to the last fraction, the denominator is currently r plus 1, so I'm going to need to introduce r minus 1. Now this is going to be a little bit problematic because the multiplication of these two polynomials is a little bit complicated. So we have a choice of either doing the clamshell method, which is addressed in an earlier video, or what I call the vertical format. So I'm going to do that off to the side where there's a little bit more room. So when I multiply these two polynomials together, I start with r cubed plus r squared plus 2r. Then I distribute the negative 1 through and get negative r squared minus r minus 2. Now I'm going to take each column and add downward. So I'm left with r cubed, the r squareds cancel, plus r minus 2. So I've now rewritten each fraction so that they have the same denominator. And now the fun part, which is to cross out the denominators and solve the resulting problem that exists in the numerators. This is going to be r cubed minus r plus r squared minus 5 equals r cubed plus r minus 2. Now the r cubes are going to cancel out. And I notice that what I have is a quadratic. And I know this because of the squared term. So to solve a quadratic, your first step is to set everything equal to 0. So I'm going to go ahead and do that now. And this quadratic is going to factor as r minus 3 and r plus 1. Setting each factor equal to 0, I get r equals 3 or r equals negative 1. But if I do a quick check, I notice that if I were to plug negative 1 in here, I'm going to get a situation that's undefined. Now plugging in 3 is fine, but the negative 1 is bad. So I'm going to put an x through this, and I'm going to reject it because it's extraneous. And our only solution is r equals 3. So just looking at this slide, there's a lot going on. There's a lot to digest. So it's important that you practice. It's important that you go slow, and it's important that you have a procedure in your mind. That procedure being figure out the LCD, rewrite each fraction in the problem with that LCD, cross out the denominator, and then solve the resulting problem in the numerator, and then finally check for undefined situations.